Good morning, everybody. Today we are going to discuss a very important, very interesting, but very difficult topic of our course. This is magnetism, magnetostatics, magnets. As usual, in order for us to understand the concepts, let's start with the history of the question. What are magnets? Long ago, in ancient Greece, stones with strange properties were discovered on the island of Magnesia. They attract iron objects. These stones are named magnets in honor of the island of Magnesia. These magnetic properties are retained by magnets for quite a long time, which is why they are called permanent magnets. In addition, an interesting thing was discovered. If you take such a magnetic stone, place it on a float, it turns out that if you turn the stone, it will turn back. That is, it always strives to be positioned in a certain way. And this can be used to navigate in space. We can see which edge of the magnet faces north. Call it H, for example. N, for example. And call this edge of the magnet the North Pole. And call the opposite edge the South Pole. You can see this example on the picture. We will get a magnetic compass with you. It was also found that like poles of magnets repel and unlike poles attract. Many years later, in 1820, Christian Ørsted lectured students on the thermal effect of current. He took a wire and passed an electric current through it, and as a result, the wire was heated. But the most interested students approached the installation after lecture, and they tried several times to turn the circuit on and off, on and off, on and off. Repeat this process. One student noticed that when the circuit was turned on, the magnetic needle of the compass began to deviate slightly. This is how the connection between an electric current and a magnetic needle was first discovered. This is the Ørsted experiment. On further experiments, it was found that around a conductor with an electric current there is some matter. We can see this matter, we can not describe it other name, only matter. It names a magnetic field. A magnetic field, what is this? We can say definition again. This is a special type of matter that occurs around moving electric charges. But then, what is magnetostatics? Magnetostatics is the study of magnetic fields in system where the currents are steady, not changing with time. It's the magnetic analog of electrostatics, where the charges are stationary. The magnetization need not be static. The equations of magnetostatics can be used to predict fast magnetic switching events that occur on time scales of nanoseconds or less. Magnetostatics is even a good approximation when the currents are not static, as long as the currents don't alternate rapidly. Magnetostatics is widely used in applications of micromagnetics, such as models of magnetic recording devices. After we understood what is magnets, what is magnetic field, magnetostatics, we will discuss with you what are the sources of magnetic field there is. There are three main sources of magnetic field in the life around us. I think you know these sources very good, and I think you saw these sources earlier and used it in your life. And maybe you used it in physics departments in your countries or in other departments, maybe in chemistry or biology or in other departments. Let's see on this. These are single moving charges. For example, electrons, you can see it on this picture, especially you can see this experiment in chemistry department, I think. So what is the next? Conductors with electric current. Conductors with electric current. I think you used, not I think, I know that you use it every time, every day at home, at classes and other departments. For example, your telephone can't work without electricity and you must charge your telephone every day, maybe more, maybe less. Your computers, your devices in kitchen and other devices. So we can say that the conductors with an electric current can be the sources of magnetic field. And what is the last, simplest source? This is magnetized bodies. These are magnetized bodies, simple magnets. Simple magnets, I think you have it at home, maybe different colors, blue and red, or maybe only metal part, and I think you used it at home in your childhood and put it with other metal devices, I think. So now let's discuss with you the properties of the magnetic field. Earlier we said the definition of magnetic field, yeah? Let's repeat it, that the magnetic field is a special type of matter that occurs around moving electric charges. So now we will discuss in the same way as we talked about properties of the electric field. To begin with, we must understand with you who can create the magnetic field. The answer is simple for you. The magnetic field is created by moving charged particles, electric current, and permanent magnets. This is the first property. What is the next? The next property is about how can we detect a magnetic field in the life around us, for example. Like an electric field, a magnetic field can't be detected with our sense organs. The magnetic field has no taste, has no smell. We don't see or hear it. We don't eat it. It can only be determined by its action. The attraction of opposite poles of magnet, you can see on the first part of picture the same pole are attract and the different pole repulse. So opposite poles attract, the second part is opposite pole are attract, second part, and the first part, the same poles of magnet are repulsion, have repulsion. I said in electric field that they are like in a life. The same people attract a pulp and the different people are attract together, yeah? So You can see it in this picture again. Different and the same. Don't forget this about it. So, the next property, we must say about next property, is about how we can depict a magnetic field on a diagram or in a figure. Everything is simple too. Like an electric field, a magnetic field can be schematically depicted using lines. We can say force lines. The direction of which is determined by the rule of the right hand or the rule of the right screw. So, we said that the force lines of magnetic field are always closed. Don't forget, please, about it. Because the magnetic field is a vortex field. In electric field will be opposite information. We draw the sun like the sunlight. Magnetic field is a vortex field, so force lines of magnetic field are always closed. And what is the right screw rule or the right hand rule? What is this? So how can we say about this rule? This is a rule for determining the direction of the magnetic field lines. The rule is as follows. If the thumb of the right hand, let's see on the picture, bent 90 degrees, shows the direction of the current, the same direction with current, then the fingers wrapping around the conductor. Let's take this conductor like as a pen, yeah? We can say okay using our hand, for example, and take in this right hand, the pen, for example, like as we wrap the conductor. And what happened? It will these 4 fingers will show the direction of the magnetic field lines. Let's see it again. No, let's see again. Like as our 4 fingers can show us the direction of magnetic force lines, like as in a picture. Let's put, for example, the conductor in hand when we show OK using our hand. The first finger show us we should put the first finger like as a current in our conductor, and our 4 fingers show us the direction of magnetic field lines. So, and in this case, the force lines of magnetic field are closed. Don't forget, please. And because the magnetic field is a vortex field, I said this information. And in this case, magnetic lines come out from the nose. Magnetic lines has no beginning and ending. They only come out from the North Pole, go out from the North Pole, and enter in the South Pole. That's all. They have no beginning and ending. They have only come on and come out and enter. That's all. Don't forget this about it. So it was the rule of right hand or rule of the right screw. And how can we draw schematically or depict magnetic lines, magnetic field using force lines? So let's see the next property. The force property of the magnetic field says that the magnetic field acts on a conductor with a current with a force called the ampere force. But before we discuss the ampere force with you, we must talk about a very important physical characteristic of the magnetic field. This is the magnetic induction, vector of magnetic induction. Vector of magnetic induction, this is a vector physical quantity, especially, this is the first. Z is the force characteristic of the magnetic field, really, it's force characteristic of the magnetic field, or we can say strength characteristic of the magnetic field, and determines the strength of magnetic interaction. Let's see the formula. How can we calculate the magnetic induction vector? Magnetic induction vector, we put letter B. Letter B. So how can we calculate it? We said that this is a force characteristic and it shows us the strength of the magnetic interaction. So we must put force, maximum force, and divided by current in our conductor and the length of our conductor. We must know the length of our conductor and current in our conductor. So after that, we can calculate the magnetic induction vector. System international units of this is Tesla. I think you know these units. Units is Tesla. Don't forget, please. And don't forget that the vector of magnetic induction at each point of the magnetic field, let's see on the picture, this is the conductor with cross. Cross is the direction of current. Cross says us that this current come out from us. So this is vector of magnetic induction at each point of the magnetic field, maybe in this point, in this point, in this point, or like in the example, green arrows, is directed tangentially to lines of force. Tangentially lines of force. Let's see. For every point of the magnetic field. For every point of the magnetic field is directed tangentially to the lines of force. Don't forget, please, about it. Now, let's return to discussion of the properties of the magnetic field. We said about ampere force. Consider a situation, for example, where a current flows through the conductor with an electric current. It acts on a magnetic needle that is nearby. But in nature, there is no simple action. In nature, there is an interaction, which means that if the current acts on a magnetic needle, then, according to Newton's third law, the magnetic arrow must also somehow act on a conductor with an electric current. It tries to move it somehow. To do this, consider an example with a magnetic field of a simple configuration. Let's say we have a magnet that creates a magnetic field from top to bottom, for example. Let me remind you that the magnetic field lines go out from the North Pole and go into the South Pole. Let's see on this picture, for example. Now, between the poles of the magnet, we place a conductor, this gray conductor with I current here. This is conductor. We put it in magnetic field, and it is acted upon by a force that we call the ampere force. This magnetic field can act on this conductor with ampere force. We call this force ampere force. We can calculate it using following formula. Let's see on this. And how can we say the Ampere's law? For any closed loop parse the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop. How can we calculate our ampere force? We should put, we have what? We have what? We have a current, we have a vector of magnetic induction, and what else? We have a length of our conductor. So it connect, we should multiply it, current on the length of conductor, on B. Again, you can see that B is a vector of magnetic induction, and we should multiply it on sine alpha. Let's see on this picture. What is about alpha? This is the angle between magnetic induction vector B and between current, this direction. This is angle alpha. And let's see, if we have sine, we must remember that the sign may be only from -1 to 1. Don't forget about it, please. So we can say that ampere force can change from minimum to maximum. Let's put in our equation. What happened? Our ampere force will be maximum when our angle alpha will be 90 degrees, because the sine of 90 degrees is 1. This is a maximum of sine, maybe. So maximum ampere force is using, we can calculate this using this formula without sine. Sine is 1. So this is the maximum when angle will be 90 degrees between current and magnetic induction vector. So when it will be minimum? Let's see. Ampere force minimum when it be 0. It can be 0. When angle alpha will be 0 or 180 degrees, because the sine of these angles is 0. So ampere force not maximum, it will be 0. It will be 0, minimum number of ampere force. So this experiment shows us that the ampere force is maximum when the current is perpendicular to the field. How can you and I determine the direction of ampere force? For this, we will use the left hand rule with you. Consider our picture on the slide, our pictures. If the left hand is positioned so that the perpendicular component of the magnetic induction is part of the hand, so enter, let's see on this picture, enter to palm, and 4 fingers show the elongated direction of current. Then the thumb bent to 90 degrees between the first finger and other fingers, shows the direction of ampere force. This is the direction of ampere force. First finger shows us the direction of ampere force, bent to 90 degrees. Let's again. Magnetic lines, let's see on this picture, must enter to a palm. After that, 4 fingers must be the same direction with the current in conductor. After that, the thumb bent to 90 degrees shows us the direction of the ampere force. This is ampere force. Like in this picture, ampere force is here. Ampere force is here. So in our case, in these figures here, we can see the magnetic lines. Let's see. Enter the palm. 4 fingers show the direction of the current, and the thumb bent 90 degrees shows the direction of ampere force, which acts on this conductor with an electric current. So let's continue. Consider with you examples of solving tasks. This is the examples. You should repeat it at home using your left hand. We should use for this rule of left hand. A big request to you at home, try again, the direction of Ampere's force with your left hand. Let's consider the first task. In first task, we need to determine the direction of Ampere force. We have a question of it. While we know that the direction of magnetic lines is from us, because the crosses, this is B, show the direction from us, for example, intercomputer, yeah? And the direction of the current from left to the right, yeah? Then, according to the left-hand rule, the direction of the Ampere force will be up. According our left-hand rule. Try to do it at home yourself without lecture. Next example. It's necessary to determine the direction of Ampere force if it's known that the magnetic lines are directed from left to right and the direction of electric current is from us because the crosses. So, according to the rule of left hand, the direction of Ampere force will be down. Let's see next example. Consider that the magnetic lines are directed from left to right and the electric current from right to left. Then, according to the left-hand rule, we try to determine the direction of Ampere force. And try to do it. But something does not work out. What happened? This is because if the lines of magnetic induction are parallel to the direction of the current, then the Ampere force is 0, because the sine of the sine of angle 0 or angle 180, what happened? Ampere force is 0, will be 0. Let's see next example. Please note that you are asked to determine not the Ampere strength but the direction of the electric current. If it's known that Ampere force is directed upwards and the lines of magnetic induction are directed to the left, then, according to the rule of left hand, the direction of electric current will be from us. We can detect it using rule of left hand. So, if we have Ampere force, we know that the first finger shows Ampere force. We should know that magnetic lines must enter to a palm, and what is about current? 4 fingers show us the direction of current. Don't forget about it, please. Next example, let's see. Please note that you are asked to determine the direction of the magnetic induction lines if it's known that the current is directed towards us. The point show the direction toward us. So current come from computer to us, for example. And the Ampere is directed to the right. Then, according to the rule of left hand again, the direction of the lines of magnetic induction will be down. And the last example is to determine the direction of magnetic induction lines. If it's known that the Ampere force is directed upwards and the current range is directed to the left. So, according to the rule of left hand, again, the direction of the lines of magnetic induction will be toward us. We should put points. It was the examples according when we use rule of left hand and detect ampere force or vector of magnetic induction and or current, electric current. So, the last property, we must say the last property of magnetic field tells us that the magnetic field can act not only on a conductor with an electric current, which we have placed in a magnetic field. The magnetic field can also act on the electric charge introduced into it. A magnetic field acts on a moving charge with a force called the Lorentz force. The Lorentz force. The Lorentz force is the force with which the electromagnetic field, according to classical non-quantum electrodynamics, acts on a point-charged particles. Let's see on the formula. Lorentz force, we put letter F, L. So how can we calculate? Let's see. It's very similar on ampere force. Opposite only charge and speed of particle or speed of electron. And in ampere force was what? Current and what? And magnetic induction vector. So, let's see. Q is charge, V is the speed of particle or velocity of particles, B is vector of magnetic induction, and sine alpha. Again, alpha, this is the angle between velocity and magnetic induction vector, not between current, like as in ampere force, between velocity of particle and vector of magnetic induction B. And we can see that again the sine alpha, and again we can say that the Lorentz force will be maximum when the angle alpha between the magnetic induction vector and the direction of charge velocity is 90 degrees. That is, when a charge flies into a magnetic field perpendicular to the direction of the lines of this magnetic field. Conversely, the Lorentz force will be zero when the angle alpha between vector of magnetic induction and direction of the charge velocity is 0 or 180 degrees. Like as in ampere force, because the sine alpha again. Don't forget please about it. And how are we going to determine the direction of the Lorentz force? How? The direction of Lorentz force is determined by the left-hand rule, as in ampere force. But there are exceptions. Let's consider them. We all know that we have two types of charges, plus and minus, positive and negative. This means that the Lorentz force will not have the same direction if we have positive and negative charges. The exception to the left-hand rule is as follows. Let's see. If we have positive charge, so 4 fingers are directed in the same direction as a speed of charge. But if we have negative charge, so 4 fingers are directed in the opposite direction as the speed. Opposite direction to the speed. So don't forget. But other is the same. Let's see. Magnetic lines must enter to a palm. The first finger, the thumb, the first finger, when the angle between the first finger and four fingers is 90 degrees, it shows us Lorentz force, and four fingers is the velocity, but we don't forget positive and negative charge. Positive charge, same direction with velocity. Negative charge, opposite direction with velocity. Don't forget about this rule, please. And consider examples of tasks to determine the direction of the Lorentz force, like as in ampere force. Let's see. The first task. It's known that we have a positive charge and it moves upward. Let's see. It moves upward. Velocity of charge is up. This means that four fingers are directed in the same direction as a speed. Don't forget. While the lines of magnetic conduction are directed at us, to us, come to us. For example, from computer to us. Then, according to the left-hand rule, and we know that positive charge we have, the direction of Lorentz force will be to the right. Consider the following example. In this example, it's known that a negative charge moves downward. So we must not forget if we have negative charge. So four fingers of our left hand rule must have opposite direction to the speed of charge. Don't forget about it. So, the lines of magnetic induction are directed away from us. Cross shows us direction from us. For example, from us to computer. And according to the left-hand rule, Lorentz force will be directed to the left. Consider example number 3. It's known that a positive charge, we must remember that positive charge, so direction of four fingers is the same with the speed of charge. So, positive charge moves upward, while the magnetic field lines are directed to the left. Then, according to left-hand rule, the Lorentz force will be directed towards us. And the last example. It's known that a negative charge moves to the left. Don't forget about negative charge. While the magnetic field lines are directed to the right. Then, again, according to the left-hand rule, and don't forget about negative charge, we understand that something is wrong. We can't turn our hand according to this example. What happened? We see that the angle between the direction of the charge velocity and lines of the magnetic induction is 190 degrees, which means that Lorentz force in this case is 0, because the sine of 180 degrees is 0. So Lorentz force will be 0 too. Now, after that, let's move on to discussing the magnetic properties of matter. We know that in our world there are many different substances and that are magnets. And there are substances that don't have magnetic properties. This is a special physical quantity. There is a special physical quantity which that describe the unequal magnetic properties of matter. This is the magnetic permeability of the substance of matter, denoted by Greek letter mu. This is the coefficient that characterizes the relationship between magnetic induction in vacuum and magnetic induction in substances. Let's see, this is magnetic permeability of matter. How can we calculate it? We should put induction in the matter divided by induction in the vacuum. And so after that we can say magnetic permeability of matter. And substances that can change the properties of an external magnetic field. They are called magnets. And there are three types of magnets: diamagnets, paramagnets, and ferromagnets. Let's consider each type in detail. Firstly, let's start with diamagnets. What is about diamagnets? Diamagnets are substances in which atoms have zero magnetic moment, less than 1, so near zero. When they are not acted upon by an external field. That is, mutually compensated magnetic moments. The coefficient mu is less than 1. And there are, for example, maybe copper, gold, silver, mercury, and they are magnets in presence of an external magnetic field, and they are capable of weakening an external magnetic field. And moreover, they don't create their own magnetic field without an external magnetic field. Don't forget, they are magnets only in the presence of an external magnetic field, and they magnetized against the direction of the internal magnetic field. Don't forget. This is diamagnets. Maybe metals. Copper, silver, gold, mercury, and other. So, what is the next? Next type is paramagnets. Metals that are magnetized in an external magnetic field in the direction of the external magnetic field and have a positive magnetic susceptibility are called paramagnets. Paramagnets are weakly magnetic substances, and magnetic permeability is slightly different from unity. There are, for example, sodium, magnesium, aluminium, potassium, you can see. Moreover, they don't create their own magnetic field without an external magnetic field. Don't forget about it, please. And strengthen the external magnetic field they can. So, and the last type of matter is ferromagnets. Ferromagnets are matters that significantly enhance the external magnetic field. The magnetic permeability of ferromagnetic materials can reach values of several 100,000. That is, ferromagnetic materials are capable of amplifying an external magnetic field hundreds or thousands of times. These substances below a certain critical temperature, the name of it Curie point, are able to possess magnetization in the absence of an external magnetic field. For example, there are cobalt, iron, nickel, and other materials. Don't forget the substances capable to have a magnetization without external magnetic field. They are magnets. Don't forget. And what is the next? Now, we must move on to discussing the next part of our lecture. This is phenomenon of electromagnetic induction. We come in our lecture from the simple material to the complex material. So, consider the situation. Let's consider the situation. Imagine that we have a magnetic field, which means there is a magnetic flux that we pass through a conductor, the cross-sectional area of which we will designate as S. Let's see on the picture. For example, we have a magnetic flux and we put this magnetic flux through the conductor, and with area S. And blue line, deep blue arrow, this is the conductor, closed contour. So let's pay attention to the figure. We have a conductor, closed loop, this deep blue. Area S inside this closed conductor or closed contour. There is N. What is about N? This is a normal vector. And the angle between S, between area and normal vector is 90 degrees. Don't forget this angle between S and normal vector. And what is about angle alpha according to this example? Angle alpha, this is the angle between vector B and normal vector in N. So, if the magnetic flux that passes through the conductor S changes, therefore, an induction current appears in the closed conductor, in the deep blue closed conductor. This is induction current will appears. From here, we express the definition. What is about magnetic induction? This is the phenomenon of the occurrence of an electric current in the closed loop when the magnetic flux that passes through it changes. Must be changing magnetic field. An electric current that is caused by electromotive force is called an induction current. This is induction electricity, induction current. So we said that magnetic flux goes through the area and we passed it through a closed loop. And we can calculate this magnetic flux using the following formula. Let's see on picture. Magnetic flux is F, big phi, Greek letter phi. And how can we calculate it? We should put electromagnetic induction multiply on the conductor cross-sectional area, this cross-sectional area S. And don't forget about alpha. We should put cosine alpha. Alpha is the angle between vector B and normal vector in. Don't forget please about it. And System International Unit of Magnetic Flux are Weber. System International Unit of Magnetic Flux are Weber. Don't forget. From the example, you and I realized that an induction current arises in a closed loop. But how do you know which direction it is? Why is this direction? Maybe this direction. How can we recognize it? How can we detect it? To do this, we will use the Lenz's rule. What is this? The induction current arising in a closed loop with its magnetic field prevents a change in the magnetic flux through this loop. And the rule L also determines that the direction of the induction current. The induction current always has such a direction that it weakens the effect of the cause that excites this current. In other words, is the opposite direction. And don't forget, I said my students every time, everywhere, that the electromagnetic induction is like a girl. I think boys understand me. That she always, magnetic induction, electromagnetic induction always does everything the other way around, like as a girl. Think about one, but do opposite. Every time, everywhere, the electromagnetic induction, like as a girl. She or it always does everything the other way around. So, don't forget about this idea. This is the main idea of the electromagnetic induction. Now, let's take an induction coil with you and connect it to a constant current circuit. In the end, nothing will happen if we have constant current circuit. But if the current in the circuit, for example, the coil, students, this is the coil, don't forget, yeah? But if the current in the circuit is alternating, then an alternating magnetic field is created around, which creates an additional induction current. Hence, we have a definition of the phenomenon of self-induction. What is about self-induction? This is a phenomenon of the occurrence then of an induction current in a circuit when the current strength in it changes. Don't forget about this. And let's look at an example in the diagram according this self-induction, according the main idea of electromagnetic induction. Let's see on this picture. You and I see that we have an electric circuit. We have electric circuit. Yeah, we have the source of current, don't forget. And we have two light bulbs. First and second are connected as well as an inductor. Let's consider the first situation and try to determine which of the lamp, one or two, first or second, will turn on first. When you and I complete the circuit, that happens that in the chain as a result. So the first was we closed the chain. Firstly, we closed the chain and current come to chain. What happened after? The current in circuit increases. Yeah, it's not like as a bathroom when we open the water. Yeah, the water come immediately. No. It must be increases, some time to increase, which means that the magnetic flux also increases too, not only the same number, increase. Therefore, an induction current arises in this coil, and which prevents the current from building up in the circuit. Electromagnetic induction, direction of current of circuit, and in the coil we have opposite direction of induction current. Why? Because we want to turn on the lamp, but electromagnetic induction does not want to turn on the lamp. Opposite direction. It must do every time opposite, everything opposite, and which means that the light bulb number 2 will turn on a little later. It turns out that the number 1 light will turn on first. It turn on firstly, this turn on secondly, because in the coil will arise the induction current with opposite direction to our current. Because we will have change in current at the beginning of the position, of the idea. So consider the opposite situation and try to determine which light will turn off first. Turn off now. When we open the circuit, the current in the circuit decreases. The magnetic flux decreases too. Not immediately zero, decreasing, changing. So, which means that induction current arises in the coil again. And don't forget about idea of electromagnetic induction. Do everything opposite, which prevents the current in the circuit from decreasing. This means that light number 2 will turn off later. It turns out the light bulb number 1 is again in the lead. It will also be turned off first. And according to this electromagnetic induction, I think you understand that this is like as a girl. It do everything opposite. We want to turn on, they don't. She doesn't want. Or opposite, we want to turn off the lamp, electromagnetic induction does not want. So, now you and I can smoothly complicate the new knowledge gained and can begin to discuss electromagnetic oscillations. Earlier, we discussed mechanical vibrations in the bioacoustic section. Mechanical vibrations or mechanical oscillations are fundamentally different from electromagnetic ones. Electromagnetic vibrations are fluctuations of charge, current strange, in an oscillatory circuit. In an oscillatory circuit, it was definition, don't forget. For a better understanding of the process, consider an ideal oscillatory circuit. An ideal oscillating circuit consists of a capacitor, let's see on the picture. In ideal oscillatory circuit, there is a capacitor and induction, coil induction, yeah, and the coil. And don't forget, if we have the ideal oscillatory circuit, that the resistance is absent, resistance is zero. This means that the oscillations in this oscillatory circuit are undamped with the oscillation period T, which is calculated by the Thomson's formula. Let's see on the picture. How can we calculate the oscillation period T? We should put 2 multiply on pi and root of L and C. What is about L? L is coil inductance. Don't forget, system international unit is Henry. And capacitor, capacitance. Or capacity of capacitor, yeah? Don't forget, this is unit, system international units are farad. Don't forget about it, please do. So, don't forget that the period depends on the inductance of the coil and the capacitance of the capacitor. Don't forget. And so, according to this ideal oscillatory circuit, let's consider with you the process of electromagnetic oscillations in an oscillatory circuit. Let's see on the picture. We have the oscillatory circuit, ideal oscillatory circuit, and we have capacitor in his and coil. What happened? Now this system without energy. Firstly, to begin with, consider with you that we take an ideal oscillatory circuit and don't forget that the oscillation in this circuit are non-damping and consider the starting point. Initially, there is no current, how I said. For this, we charge the capacitor. We give the energy to our capacitor. What happened after? That is, it turns out that the electrical energy in the circuit is maximum electrical energy because all energy now are in capacitor, but magnetic energy is zero. Because the maximum charge is concentrated in the capacitor and the charge in the inductor is zero. We don't forget that the capacitor have two different plates, yeah? And it has two different charges of plate, minus and plus. Firstly, voila, we give that this is plus, this is minus. So, what happened after? The process does not stand still. What happened? The capacitor is discharged and a current appears in the coil. Increasing, yeah? The coil in coil. Don't forget that the charges come from the plus to minus. The direction of current will be here, from plus to minus. What happened in the second stage? In this second stage, there comes a moment when all the current, all energy, all charges was in coil, were in coil. And the charge in the capacitor is zero. Let's see. Energy in the capacitor is absent. All energy now in the coil. In the coil. In this case, the magnetic energy is at its maximum and the electrical energy is zero. Then, in this situation is not stopped. What happened after? Then the capacitor is charged again and the sign on the plates is reversed. Let's see. Left part was plus, left part was minus. Now it's minus. Don't forget opposite, because the current come from plus to minus, and plus come on this plate. Don't forget. So, and again, yeah, don't note that it was assumed that the current goes from the positive pole to the negative, which means that the capacitor plates were charged with the opposite signs of the initial charge. And in this third case, in this case, the electrical energy is again maximum. Electrical energy is again maximum. And magnetic energy is again zero. So then the capacitor is discharged again, discharging. And what happened? A current appears in the coil again, and the magnetic energy is maximum and electric energy is zero. What happened after? Then the capacitor is charged again and we returned to the initial stage when the charge of the plates was like this, like this. Thus, there was one full oscillation or one complete oscillation of the charge in the oscillatory circuit. Don't forget. And don't forget, we know that the period, what is about period? This is the time of one full oscillation, one complete oscillation is t. We should divide our oscillation by 4 stages. And so, according time, we should divide it on t by 4. First stage is 0 stage. This stage is 1.4 stage, 1 by 4 stage. This is half, 1 by 2 stage, and 3.4 t. And after that, again, full direction is here. This is 0. Don't forget, please, about it. So, but this is undamped oscillation in an ideal oscillatory circuit. In real life, an ideal oscillatory circuit does not exist. I think you know this. And since there is no situation when the resistance is completely absent, this is not our real life. So, this is only model for best understanding. Let us now consider the situation with a real oscillatory circuit. Look at the picture. A real oscillatory circuit contains not only an inductor and capacitor. Also, it has a resistance R. It has a resistance R, and so we can say R is not zero. R is presence. R is presence. This means that the oscillations in such a circuit are damped. Thermal energy is released on the R resistance conductor, which can be calculated using the Joule-Lenz formula. Let's see. We know that our electric devices, when they worked, it is heating, after some time. How can we calculate the energy, how much energy was? We should use Joule-Lenz formula. How we can calculate this energy Q? We should put our current in square. We should put resistance of our conductor and time. How much time it worked, for example, our electronic device. And after that, we can say how much thermal energy how much thermal energy was, for example. And the graph also shows damped oscillations when the resistance in the circuit is not zero. Dependence between ampere is current, between time. So it was electromagnetic oscillations. We have understood what electromagnetic oscillations are. Now we have to consider electromagnetic waves. You can say me that in the bioacoustic section we already talked about waves. Yes, I agree with you, but there was mechanical waves. Specifically, we talked about sound, for example, and we said that sound is longitudinal mechanic wave which spread in an elastic medium. In an elastic medium. We said this definition. I agree with you, really. But electromagnetic waves is not mechanic waves. We said that electromagnetic waves can spread through the vacuum, but mechanic waves cannot spread through the vacuum. I think you know this. So we have to discuss what electromagnetic waves are. As usual, let's start with the definition again. Everything starts from definition. What is about electromagnetic waves? Electromagnetic waves are magnetic field propagating in space. Electromagnetic waves occur due to the fact that an alternating electric field generates an alternating magnetic field. In order to create an electromagnetic wave, a special condition is required. Don't forget. For example, if we have mechanic waves, we said that we must have the source of vibration. For example, what happened? For example, maybe our voice, For example, we describe our voice and say that the sources was, for example. What is about electromagnetic waves? What is a special condition? Namely, it's necessary that there was not just the movement of electric charges, but there was an accelerated movement of electric charges. We said earlier about electromagnetic oscillation. These are fluctuations of charge in oscillatory circuit. But what is about electromagnetic waves? These electric charges can go with acceleration. And as a result of this, you and I will be able to receive an electromagnetic wave. Don't forget. So, knowing now the definition of electromagnetic waves, we must consider the law of electromagnetic induction from a new angle, from other angle, yeah? Generalizing the laws of established experimentally, Maxwell developed a complete theory of the relationship between electric and magnetic fields. A single electromagnetic field which made it possible to predict the existence of electromagnetic waves, calculate the speed of their propagation, and then create an electromagnetic theory of light according to which light is such a wave. Yeah. On the last lecture, we said that lights can spread through the matter like as an electromagnetic wave, and so, according light waves, Maxwell describes some laws about electromagnetic theory. So, Maxwell introduced the concept of a vortex electric field into physics and proposed a new interpretation of the law of electromagnetic induction. We said that electromagnetic induction, like as a girl, yeah, each do everything opposite. A new idea what? Let's see the first point. Any change in the magnetic field generates a vortex electric field in the surrounding space. The lines of force, or we can say force lines, of which are closed. Let's see. If we have violet arrows is magnetic field and black arrows is electric field. So we have a changing magnetic field, yeah? And any change of this magnetic field generate a vortex electric field. Earlier what happened? We draw not vortex electric field, yeah? We draw it like as a sun. Now, according Maxwell's law, we can say that my electric field in the surrounding space, which magnetic field generates, is vortex, and the lines, the force lines, or the force lines of which are closed, like in this picture. So, what is the second point? A time-varying opposite point. A time-varying electric field creates a magnetic field in the surrounding space. So, opposite point, yeah? If we have change in magnetic field, we can create a vortex electric field. And opposite, if we have change in electric field, it can create us magnetic field in the surrounding space. This is Maxwell's law. This is a new interpretation of the law of electromagnetic induction. And we must remember with you that if at some point in space a charge performs harmonic oscillations, then it's a source of an electromagnetic wave. I put it nota bene, yeah, not bien, nota bene, that this is very important for us. We must remember that if at some point in space the charge performs harmonic oscillation, then it's a source of an electromagnetic wave. Please don't forget about it. An electromagnetic wave is a process of sequential interconnected change in the vectors of the strength of the electric and magnetic fields directed perpendicular to the wave propagation beam, in which a change in the electric field causes a change in the magnetic field, which in turn cause changes in the electric field. Consider an electromagnetic wave. Let's see on this picture and again this picture. Electromagnetic wave have three components. Because this is not simple wave. This is a complex wave. It consists from three parts. Let's see. For example, we should put our three fingers, yeah, and between first, second, and third finger between everybody will have the 90 degrees, yeah, for example. And all over three fingers, they shows us 3 points or 3 components about our electromagnetic wave. What components? Let's see. First component, along the OX axis, the Z axis, what happened? This is the direction of wave propagation. This is the velocity of wave. Direction of propagation. So, what else? What is about OX line? This is the red part. This is electric component. Let's see. Electric field component. Electric field, strange, we said it about it earlier when we say about electrostatics. So, and last is X was a B component. Sorry, I'm so sorry. X was a B component. What is about B component? This is the magnetic field component. What is about B? This is a magnetic field strange vector. And E is Y component. This is electric part, electric field strange component. Velocity is green arrow. Don't forget. And don't forget that. So in the when we said about bioacoustics and when we said about mechanic waves, we said the physical characteristic of waves. So it was amplitude, period of time, yeah, frequency, and other velocity, wavelength. So electromagnetic waves are waves too, and so they have a velocity, they have a direction, they have a wavelength, they have a period. But when we said about bioacoustic, how we calculated the period of time, we should put 1 over hertz, yeah, 1 over frequency was. What happened? Very simple. But about electromagnetic waves, don't forget, we should put Thomson's formula. Don't forget about it, please. We must know the inductance of coil and capacity of capacitor. And don't forget about wavelength. In the bioacoustics in mechanic waves, we said that wavelength is the length of one full vibration, one full oscillation. The same in here too. The wavelength lambda, this is the length of one full oscillation. How we can calculate lambda? We should put velocity of our wave multiply on the time of our wave. This is not x, lambda letter, Greek letter lambda, velocity v multiply on period. That's all. It will be the wavelength of our electromagnetic waves. This is one full vibration, one full oscillation. So I can say you thank you for the attention, and I must remember that please don't forget about our lectures. Don't forget see it on my YouTube channel, and don't forget ask me or ask Arina Viktorovna about components of lecture if you don't understand some situations, or maybe you don't understand some points of lecture. Thank you for the attention again. Goodbye.